Hello everyone, welcome back to 3 Deviations. In today's video we are beginning Unit 6, and this is probably my favorite unit of single variable calculus, because in this unit we get to talk about the techniques of integration. So the techniques of integration involves how we can determine the antiderivatives of some really complex functions. And to do that, we are going to use some pretty cool techniques, one of which is integration by parts, which we are going to introduce the derivation for today. So let's get ready for my favorite journey through Calculus 2, the techniques of integration. So, as I said back in Unit 4 when we started with the substitution rule, each of the differentiation rules that we have in single variable Calculus 1 have a rule for integration, maybe with the exception of the quotient rule. But we are going to now talk about the reverse product rule. So to do that, I would first like to talk about the product rule for differentiation, and then we're going to derive the integration by parts rule, which is really the product rule for integration. So as I said earlier, I recommend for these videos that are coming up that you should know your integral functions, like your antiderivatives, and you should also be extremely comfortable with the substitution rule. Okay, so let's get started. So the product rule says that if I want to differentiate the product f of x times g of x, that's going to be equal to the derivative of f of x times g of x plus f of x times the derivative of g of x. So what I would like to do now is simply integrate. So we are going to throw integral signs over all of these guys, and then we'll put one there too. We'll put one there as well. So when we integrate these guys, what we need to be careful of is that we have some functions that where the entire integrand is being differentiated. And we have others where only part of the integrand is being differentiated. So we can't fully integrate the two on the right side, but we can fully integrate the one on the left. So if we fully integrate the one on the left and we do a little bit of rearranging, we are going to set f of x equal to u and g of x equal to v so that we can more easily see this rule. We are going to end up with the integral of u times dv is equal to u times v minus the integral of v du. So as you can see, what we did here is we really just took this guy here, and then we subtracted this guy here. So now what we can do is we can maybe take a little bit of a look at how this is applied. So again, as I said maybe back when we started Calculus 2, that these units are going to be a little bit conceptually difficult, and that's okay. We're going to do tons of examples with integration by parts. But this is one of the easier integration techniques that I think should be pretty easy to grasp just once we get some of the intuition down. So we are going to now discuss picking u and dv. So as we said, the integral by parts rule, the integration by parts rule, says the integral of u dv is equal to u times v minus the integral of v du. So basically, the idea here is that this is an integral that we can't do, right? So if I have u and dv, so dv is really a function times dx, I can rearrange it and integrate dv and differentiate u and end up with this integral, and then this is just some algebra here. But we'll end up with that integral. So basically, the deal is that u should be a function that's easier to deal with once differentiated, and then dv should be a function that is doable when integrated and is able to be integrated. So basically what we're doing is we're isolating a more tricky integral like the dv that we have and putting it into something where it is maybe not with as many constants or algebraic terms. So this is what the bracket looks like. We pick a u here, and we pick a dv here, and if it's a dv, it always has a dx on it, and if it's a du, it always has a dx. So what we do is when we find u and dv, we integrate dv to find v, and we differentiate u to find du. So now let's talk about which functions we should pick. So there's a rule, a convention out there in the Calculus 2 world that goes by the name Lyautey. So I, A, T, E. Okay, so what does this stand for? So L stands for logarithmic functions, so log. I stands for inverse trig. A stands for algebraic. T stands for trigonometric. E stands for exponential. Now let's go over why this is the case. So this is going up, so this is what we really want to pick for our U. This is what we don't want to pick for our U down here. So let's go over why these are good things to pick for our U and bad things to pick for our U. So the logarithmic, inverse trig, and algebraic functions, these are all functions that when I differentiate them, they become a lot less tricky. So if I differentiate a logarithm function, like the natural logarithm, that becomes 1 over x, right? And then if I differentiate inverse trig functions, well, they become 1 over square root or 1 over 1 plus x squared. They become those types of functions, which are easier to deal with. The algebraic, I really think algebraic might go to the top, but let's say I have something as a u like 2x. Say that's my u, and that's attached to some crazy f of x that I don't want to deal with. So I have an integral of 2x times f of x dx. Well, if I pick u to be 2x, then du is just going to be 2. So then when I'm doing this harder integral over here, then I can completely isolate the v, and then the du is just going to become a constant term on the outside of the integral. So that's going to be way easier to deal with. So you might be now seeing why this is a better choice of u than something like a trig or exponential function. Now the problem with trig and exponential functions is that when you differentiate them, they don't necessarily become easier. For example, differentiating trig functions, they can even become messier. Differentiating sine is just going to go in a big feedback loop, and then differentiating e to the x is just going to stay e to the x. And then if I differentiate something like 2 to the x, that also becomes fairly tricky. So we don't want to deal with those. So that's why we pick this Liate rule. So if we have a log, inverse trig, or algebraic function, then we pick it as our u. And if we have a trig or exponential function, then we probably want to pick that as our dv. All right, so in the next video, we're going to go over an introductory example with integration by parts, and this should clear a lot up for us. Thank you for watching, and we'll see you in the next video.